Okay, let's go ahead and get started. Welcome to Friday morning. It's hard to believe we've already at September 25th. So hopefully you're doing well on this Friday morning. I wanted to start out very briefly with just something that we looked at in the last lab. And that was with the oxygen and its molecular orbitals in Spartan. So thank you all for working through getting Spartan up and going. It's a great program. The VPN has added a little extra layer of complications onto things this year, but I think everybody is there. By the way, if you want to do a quick check to make sure the VPN is working, before you start the VPN, in Google, just type, "What's my IP?" It'll tell you what your internet protocol address is, your IP address. Once you're connected to the VPN, that will change. And so you can just refresh it and see, did your IP address change? Because it becomes Emory's IP address. But anyway, several of you noticed something that looked a little bit funny about oxygen and how oxygen was calculated. And so when we draw the molecular orbitals, we've got the two bonding molecular orbitals. And then the HOMO and the LUMO, really we should have two pi star orbitals that are the same energy. And it's this orbital, and then rotated 90 degrees, this orbital. Because of the way that Spartan is minimizing its energy, it actually gets this calculation wrong. Okay, it interprets it not in the way we traditionally do in organic chemistry. It's not wrong, it's just, it minimized the energy a little too far. So these two, what's listed as the HOMO and the LUMO, if you notice, they both look like pi star orbitals just rotated 90 degrees. That's what we would traditionally draw as being each singly filled with degenerate energies. You can force Spartan to do that by saying you have two unpaired electrons. We didn't tell it to do that, so it paired them up and put them here. So I just wanted to say that's why those looked a little bit funny to those of you who were looking at that carefully and wondering why it didn't quite connect to what we'd seen before in class. Okay, so today, though, we're going to keep going, and we're going to be looking at a couple more techniques. So this really gets into this idea of, okay, you ran a reaction, what did you make, and how do you know what you made, right? We talked in the last few weeks about how to separate mixtures or analyze reaction progresses or reactions that are going on. Today, we want to talk a little bit different. We want to talk about, you've run your reaction, how do you know what you got? How do you know what you made? Especially if it's a reaction that nobody's ever done before. How do you know what you're looking at here? So we're going to look at two techniques, mass spectroscopy and infrared spectroscopy this week. And then next week, we're going to look at nuclear magnetic resonance, or NMR. Those three techniques combined are the most common techniques that are used in synthetic labs or for analysis and things like that. So these are kind of the three big powerhouses of the way we look at chemical reactions and figure out what went on. All right, so mass spectrometry is where we're going to start and what it's used for. And I want to talk just briefly about some of the things that that you work with this. Now, you've actually seen mass spec a little bit because you saw it back in Chem 150. Right? When we were talking about isotopes and things like that, we talked about that. So looking at isotopic ratios and things like that is there. But this is a really common technique that's used not just in chemistry, but in other areas. If you ever hear when they're testing for steroid use, we canceled the Olympics this year, but it'll be coming up again. So things like that, that's done with mass spectrometry. Much environmental testing, when we look at pesticides, are there pesticides in the groundwater or soil, things along those lines, that's done with it. If you ever gone to the airport and they do that swab across your hand or on your backpack or your suitcase, and they take that little circle and they put it in a machine, that machine is a mass spectrometer. So that's the what they're doing. They're looking for explosive molecules or drugs or other things like that. It's very good at doing that, comparing it against a library of known compounds. When I was a graduate student, my desk was actually in the research lab. We don't do that anymore, but it was. And a couple times security said they wanted to do an extra scan of my backpack, and they had to do it like 4 or 5 times because it was covered in all sorts of stuff from the lab. So, but they were using mass spectrometers to do that. And then also, you'll hear a lot of things we talk about, oh, water found on Mars or water found other places and things like that. Since about 1972, it's when we sent our first mass spectrometer in space. And this is what we're using for that. It's on the Mars lander. And also, I'm sure that Elon Musk will bring one with him when he goes to Mars. So really useful technique for a lot of things. So how do you do it? Well, it's got 5 parts to it. You take your sample and you need to vaporize it. So this is one of the limitations to mass spec, is that whatever you analyze has to be in the gas state. So somehow you've got to get it up to the gas state. So we vaporize it usually by heating it up. So we've got some sort of an oven in here. So if you have a really big molecule or something that's temperature sensitive, this is not going to work for you. Because as you heat it up, you might break it apart. So like it would denature a protein or something like that. But you got to get it into the gas phase. And then the second step is to ionize it. We need to have ions. So there's many different ways to do the ionization. This is the electron beam. It is the most common. There's chemical spray. There's all sorts of different ones. And if you really want to get into mass spec, you can talk about why you might use one versus the other. But somehow you have to ionize your material, because the third step here is to accelerate it. So what we've got is you've got this gas over here that's kind of in the oven that's being ionized. And then what we do is we knock electrons off. I'll show you that in the next slide, but we make it positive. So then we have a negatively charged metal plate here. Well, that means these particles are going to be attracted to that metal plate. So they accelerate towards that metal plate. Then we have a little tiny slit in here just to focus it. And usually there's at least 2, if not 3 or 4 or more of these. And every one of them causes the molecules to move faster and faster because they're attracted to those plates. And it focuses the beam down tighter and tighter, so we get better resolution. We get smaller and smaller slits. So you get your charged particle. You accelerate it by attracting it to a plate that has a negative charge. And some of the molecules slide right through that plate because there's a hole in it. So you get it going really, really fast. And then the heart of how a mass spectrometer works is this deflection area. So it passes through some really strong magnets. Remember, electromagnetic radiation, things with electric charges are affected by magnetic fields. So as it goes through this magnetic field, it's going to be bent by the magnetic field. And it's how much it's bent is affected by 2 things. One, just how heavy it is, right? Heavier things are going to be harder to deflect. So heavier things are going to tend to want to go more straight. And the higher the charge, the more interaction with the magnetic field. So the higher the charge, the more it is deflected. So what actually determines the amount of deflection is the mass and the charge. So we actually do it based on the ratio of the mass to the charge, right? So you'll hear us talking about the M to Z, that's mass to charge ratio a lot. So things that are heavy tend to not be deflected as much, but the higher the charge, more deflection. And then finally, we have some sort of a detector, some way to see this. And so assuming everything has, let's say, just a +1 charge, the lightest ions are going to be deflected the most, so they're going to appear over here on the left. The heavier ones are deflected the least, and they're going to appear over here on the right. Okay, so based on the mass, it ends up splitting it. So that means that if we have different size, different masses of atoms or molecules, we should be able to split them and see those as they come through the instrument. All right, so how do we ionize it? Very briefly, just putting this up here because this reaction in the bottom is important for us. So we take our molecule somehow, usually with an electron beam, we actually shoot electrons at it, which knocks other electrons off. It doesn't actually give it a negative charge. It gives it a positive charge, which is a little bit weird, but it does. And so we end up with this molecular ion, and we'll talk about the molecular ion quite a bit. It's a radical cation, so it has 1 electron that's been removed, so 1 is left over, so that makes it a radical. If you started with a radical, it would lose the radical, but very few things are radicals to start with. So usually we end up forming the radical, and we've got the positive charge. And remember, that positive charge is important because that's how the magnet deflected it. So we can actually only detect things that have charges on them. So we've got to have that. Okay. All right, so what does one look like, right? Now, back in Chem 150, we didn't look at very exciting mass specs. We looked at like bromine and chlorine and things like that. And we saw that there were multiple peaks, right? You saw a peak at 35 and 37 for chlorine. So we could tell that there were 2 isotopes. We could actually tell the relative ratios of them and things like that. But here's hexane, and hexane is what I'm looking at here. That's a long chain of 6 molecules. And so several things I want to point out on this structure. The first here is what's called the parent peak or the molecular ion peak. That's the highest one. And that, if you notice, matches the molar mass of our compound, pretty close. This is a low res magnetic or mass spec, so we only have whole numbers on here. It's mostly what we're going to work with here. And so this peak here at 86 represents the loss of the electron. That's the whole molecule. Then you'll notice that there's a whole bunch of other peaks, because it turns out when we heat this thing up and we ionize it, we actually blast the molecule into pieces. And those pieces tell us more about what the molecule was than anything else. So what you're going to see is a common theme through this week and next week is that it's like a really big jigsaw puzzle. We're trying to put together all of our pieces and all of our evidence to figure out what happened. So in mass spec, you take a molecule, you blow it apart, and you see what you got, and then you try to figure out how could that come together to form a molecule. Let me walk you through that. So with this, we've got the parent molecule of 86. But then we get peaks at 71, 57, 43, 29, and 15. And we got to figure out what are all of these fragments? What are these pieces? And so if you look at 86 minus 71, what fell off to get from here to here? Well, it's 15. 15 is, well, that's a carbon and 3 hydrogens, okay? So that would weigh 15. So maybe we lost a methyl group to go from here to here. And then these are all kind of like 2 atoms that are CH2s. So let me show you that. So let's look at the molecule and the spectrum again. All right, so if we start over here on the left, if we have the whole molecule, we just give it a charge, it's gonna weigh 86. If we lose this methyl group, so if we break, let's say carbon 1, 2, 3, 4, 5, and 6. If we break between carbon 5 and 6, we're gonna get one fragment that weighs 15 and one fragment that weighs 71. Well, there's our 71 and there's our 15. But if you break here between carbons 4 and 5, you're going to get a fragment that weighs 57, and then a fragment that weighs 29. Okay, there's our 57 and 29. So you can see where the molecule has broken, and those pieces, how they would fit back together to make our full hexane. Is this the only thing you could make with these fragments? No, you need more than just mass spec, because mass spec just gives you a bunch of pieces. And sometimes you can put your puzzle back together in more than one way. So we're going to need a little more data, but it can give us that information. One other term that you're going to hear is something called a base peak. The base peak is whatever the highest peak is. It's the most commonly formed fragment. And so, because you can break here or break here. These are actually pretty close in their relative amounts, but see a little different. Okay, so that's N-hexane. If we break it up, really simple, just a straight chain. So what if we now branch that chain? Let's look at N-hexane, which is on the top. That's what we just talked about, 86, 71, 57. And let's do 2-methylpentane. Now, think for a second, what is 2-methylpentane? 5 carbons with a methyl group. So it's still C6H14, same chemical formula, but we've got a branch in it now. And what we can see is the pattern changed. We still get peaks at 86, 71, 57, 43, etc. But this peak at 57, not very common anymore. We don't get the molecule breaking that way. In fact, what happens is that it almost always breaks to give us a 43. And then this 29 down here. Now, there's a lot of other little peaks. And some of you are kind of looking at it going, what are all those little peaks? And we're not going to get into that very far, because when you blast this thing and blow it apart, all sorts of other chemistry can happen. There are rearrangements. There's methyl shifts and hydride shifts and Michelson rearrangements, and because we have to put names on everything in organic chemistry, and all sorts of things like that. We're not going to worry about the little peaks. We're just looking at the big peaks at this level, because they can tell us enough information. So we get similar peaks from N-hexane versus 2-methylpentane, but we have a different relative abundances. So how can we explain that? Well, let's look at our structures here, and let's look at 2-methylpentane. All right, so once again, here's my molecule, 1, 2, 3, 4, 5, 6 carbons. Still have my, as I said, C6H14. But let's think about this. Now, you know from class, from 202 and 203, that carbocations have relative stabilities, right? A primary is the least stable, secondary is better, tertiary is the most stable carbocation. That's still true in the mass spectrometer. So if you're breaking your molecule apart, it's going to tend to break in ways that give you the more stable cation. So if you can make a secondary versus a primary, that's going to be better, right? So if you look at that, here's our 2-methylpentane. If we break the molecule right here next to the branching, then what we're left with is this branched carbocation. Well, that's secondary, that's good. And that's going to give us masses of 43 and, well, actually 43. Both of these are ethyl groups essentially, and that's where we get this nice big peak here at 43. That's the most stable. Now there is another way to get a secondary, which is instead of breaking right here next to this bond, we just lop this thing off right here. We essentially lop the branched methyl group off, and we get this long chain here, and that's going to give us our 71 and our 15. You don't always see the ones at really low mass, they get lost sometimes. But this explains to us why 43 and 71 are the predominant peaks now, because there's two ways to split this molecule that give you a secondary carbocation that's more stable, so that's what your molecule does. Okay, so it's not just what peaks you've got, it is also where they are in their relative abundance. So you're faced with a new mass spectrometer, or mass spec. You've got a spectrum here. What do you do with that spectrum? Okay, so how do we go from, let's say we looked at, let me go back here. We looked at this, we found out our parent peak was 86, and we didn't know that this was what it was. How do you just go from a mass to a formula? Now for carbon-containing compounds, we do this with something called the rule of 13. Essentially, people sat down and they looked at molecules, and they looked at a lot of molecules, and then they looked at a lot more molecules, and they realized that, well, you know what, if we do this process, we're going to get to our chemical formula. It's just algebra, looking at the fact that a carbon weighs 12, a hydrogen weighs 1. So they're essentially saying how many carbon-hydrogen units are there. So what you do, and I'll go through an example here in a moment, is you take your parent mass, the biggest peak, and you divide that by 13. The quotient represents the number of carbons. So the whole number you get is how many carbons are in your formula. And then the remainder plus the quotient is how many hydrogens. Because remember that 13 is a carbon and a hydrogen. And then we have to check to see if it makes chemical sense. Now that works if you only have carbon and hydrogen, but you know, a lot of molecules have other things too. What if you have an oxygen? Well, you need to know you have an oxygen somehow. And we're going to talk about in a minute how infrared spectroscopy can tell you that. IR can tell you this, elemental analysis can tell you this. We never use just one technique. We often have a lot of techniques. So if a compound has an oxygen, what you do is you determine your formula with the rule of 13. And then you say, no, wait a minute, an oxygen weighs 16. So I'm gonna add in my oxygen, I'm gonna take out 1 carbon and 4 hydrogens, because that also weighs 16. So you just swap an O for a CH4, because those have the same mass. Likewise, if you have a nitrogen, now nitrogen gets a little funny, right? Nitrogen weighs 15, but we actually swap a CH2. That's just empirically what works. But one thing you can think about is that if you have an odd number of nitrogens, you're going to get an odd molecular mass. Whereas if you have an even number of nitrogens, you get an even molecular mass because nitrogen weighs 15. So there's just some things you can get from that. So let me walk you through this calculation. And in just one moment, I've got one more thing I want to tell you that helps you. Once you have your formula, we're going to use this a lot, which is how do you turn that into a structure? And the number of unsaturations, these are how many double bonds or rings you have. This is a weird formula. Take 2 times the number of carbons plus 2, plus the number of nitrogens, minus the number of halogens, minus the number of hydrogens, divide all that by 2, and that's your number of unsaturations. It works. It's algebra. So like, for instance, if you had C5H10, then you'd have 2 times the number of carbons, so that's 2 times 5, plus the number of, or plus 2, plus the number of nitrogens, none of those, minus the number of halogens, none of those, minus the number of hydrogens, divide all that by 2, comes out to 1. So that means you have 1 unsaturation. So when you're building your molecule, you know that you have either a double bond or you have a ring closing. A triple bond counts as 2 unsaturations because it's the 2 pi bonds. So any pi bond counts as an unsaturation. So in theory, what we've got now is a way to go from a molar mass to a chemical formula. Okay? So we can use the rule of 13 to figure out our chemical formula, assuming it's only carbon, hydrogen, oxygen, or nitrogen, which is a lot of organic chemistry. And then we can use the unsaturations to tell us a little bit about the bonding with it. All right, so let me walk you through an example. I was going to write this out for you, but iOS 14 broke Zoom, so I can't do that. So we got to do it here on the slide, but that works. And so let's look at this. What if you have a molar mass of 108. So your parent peak is 108. What do we do? Well, all right, 108 divided by 13 is 8 with a remainder of 4. So you get like 8.3, something like that. All right, so what does that mean? That means that, remember that the number of carbons was the 8, and then the number of hydrogens was the factor plus the remainder. So 8 plus 4 is 12. So we get a formula of C8H12. That weighs 108. Okay. Now, what if we look at the unsaturations and we look at that and we plug it into that formula I gave you a second ago, and we'll find out that there's 3 unsaturations. So you could have 3 double bonds, you could have a ring, you could have 3 rings, you could have a triple bond and a double bond, right? There's a lot of combinations, but you know you're gonna have some unsaturations. Now, what if you also had a heteroatom? What if you had some oxygen in it? So here's what you do if you have an oxygen. We said that you take out a methyl group or a CH4 group because that weighs 16 and you add in an oxygen. So we took out 1 carbon, so we went from C8 to C7, and 4 hydrogens, so it became C8 and O. This also weighs 108. So if your formula had an oxygen, it could be this. If it had 2 oxygens, well, we can just do that twice. What if it had an oxygen and a nitrogen? Okay, so you can see there are several options here. And you might be looking at it going, well, how do I know which one it is, right? Well, we can use the spectrum and we can use IR and some other things. But just by knowing the mass of the compound, we have narrowed it down from all thousands of different compounds and possibilities to 4 possible chemical formulae, right? That's not bad, right? That's some good narrowing down. So it's probably C8H12 or C7H8O or C6H4O2 or this one here. So then we'll do some more techniques there. But knowing the molar mass can really narrow down what your compound can be. All right, let's look at another one here. Let's look at 144.2. So we run it through the mass spectrometer. That's the mass we get. And so we do our rule of 13, and we get 11 with a remainder of 10. And to answer the question again, the M to Z ratio, we're going to assume that it has a single plus charge, so that corresponds to the mass of the main peak because it just has a 1 charge on it. So we get that. You can get more than 1 charge. We're not going to go that far. Okay, so you get 11R10 here. So if we do the rule of 13, that gets us C6H16. And I challenge you to try to draw a molecule that has 6 carbons but 16 hydrogens. You can't do it. It doesn't make any chemical sense. You can never be higher than the 2n plus 2 rule, right? So something is a little funny in our math here. We have to think about that. And so we say, okay, that didn't quite make sense. Well, what if we just had an oxygen? What if we took out 1 of those carbons and 4 of those hydrogens and put in an oxygen? Well, then we get C5H12O. And that is a molecule that makes sense. And then, so you got an oxygen, and we can use infrared spectroscopy to determine whether we have a carbonyl, an alcohol, or an ether. So we'll see in a minute that infrared spectroscopy tells us about which functional groups are present. So as kind of a reminder here, mass spec only gives you molecular weight data. We have to use other techniques to tell us things about, do you have a heteroatom present or not? What form is it in? But that molecular weight data tells us an awful lot. So that's why we like that. Okay. Yeah, C6 makes no sense. There's a typo there. Where's my calculator? Somebody just asked me, somebody checked my math while I was going, and that's a good idea. The problem is I changed examples partway through, and then I forgot to fix it. So we get 144 divided by 13 is 11R1. Yeah, I changed my wrong number here. Okay, I will send out an updated one of these. I want to keep the flow going, but you're right, that number doesn't make any sense. Thanks, Professor Mulford. Okay, send you out an updated one. All right, let's work on one that I know does work, okay? So you go into the lab and you do this molecule and you get this spectrum and you look at it, and from this, you're supposed to be able to figure out what's going on. Well, not quite. We need a little more data. So we look at the parent peak. Remember, base peak is the one that you have the most of, but parent peak is the highest molar mass peak you've got. So we have a mass of 134. So we can do the rule of 13 here. And we're going to get C10H14. However, we go into the lab also and we do take an infrared spectrum, and we get a carbonyl. So we know there's a carbonyl in here, okay? And then we also, so we propose instead of C10H14, if we have a carbonyl, we've got to have at least an oxygen. So I'm going to propose C9H10O. I don't know exactly, maybe there's 2 oxygens, but we're going to start here. And we're going to say, I'm going to guess this one here, C9H10O. And then I do the number of unsaturations. I do that formula I gave you, and it comes out to be 5. Okay, 5 is a lot of unsaturations. 5 double bonds, or 4 double bonds in a ring, or something like that. But when I'm trying to piece my molecule together, it's important for me to remember that I need these in my molecule. They're kind of my puzzle pieces. Okay. So, and to repeat, I had a question on this asking to clarify. The parent peak is the highest molecular or the highest mass peak. Molecular orbitals on the mind. And then the base peak is just whatever the tallest peak is. That's the most common fragment that you get. So you've got the parent and the base. Okay, just the 2 terms there. All right, so if you know the mass is 134 and you know that you've got a couple options on the formula and your unsaturations, how do you turn this into a structure? What do we do with this? Okay, so let's look at this. Let me walk you through this. All right, so let's zoom in on a couple of things here. All right, let's look at the base peak, again, your tallest peak of 105. Where do we get that? Well, what I want to do first, I want to say, okay, how do you get to 105? I don't want to talk about what 105 is yet. You can, but I want to start with just, well, how do we get there? Well, 134 minus 105, so our parent peak minus our base peak, means that to get there, we had to lose a fragment that weighed 29. We do the rule of 13 on 29, and you get C2H5, which is an ethyl. All right, well, that could be a pretty common group, right? You've just got a C2CH3, CH2CH3. Okay, so probably to get from the parent peak to the base peak, we lost an ethyl group. Then let's look at that peak at 77. And we can either say, how did we get there, or what is it? I started to say, how did we, or what is it? So we use the rule of 13, and it gives us C5H17. And again, that's crazy. That's over the number of hydrogens we need. So 17 hydrogens, that's likely a carbon and 5 hydrogens. So let me try that. Let me say, let's do that. Now, when does this happen, by the way? If you have a high number of unsaturations, you often have to do this type of an adjustment because we're missing some hydrogen. So our masses ended up being a little off for rule of 13. Rule of 13 assumes unsaturated, or completely saturated, excuse me. All right, so if that's the case, if C5H17 doesn't make sense, but I say, well, 17 hydrogens, that could be a methyl or a carbon and 5 hydrogens, that means my formula is now C6H5. Well, C6H5 might ring a bell for you because C6H5 is just an aromatic ring. And an aromatic ring is a closed ring, so that's 1 unsaturation, and 3 double bonds. So that would account for 4 of my 5 unsaturations, right? That seems to make kind of sense. And C6H5, a very common functional unit, and it would weigh 77. So I'm gonna say that's probably it. Now, how did I get to 77? Well, 134 minus 77 is 57. As you can see what I mean by puzzle pieces, where you're just kind of playing with the numbers here. And I look at it and say, okay, well, if the formula was C9H10O, and the 77 peak is C6H5, well, what I'm left with is C3H5O. And we know from the infrared that we have to have a carbonyl. Now, why did I say that? Because I know that it's not, I'm not going to propose an alcohol or an ether, because I know I have to have a carbonyl. So I'm going to say, okay, I probably have an acyl group, because I've got to have 3 carbons, 5 hydrogens, and an oxygen. So here's my 3 carbons, my 5 hydrogens, and an oxygen. And I know I have to have that double bond to an oxygen. All right, so that's what would give me my acyl group, okay? And then what does that mean? Okay, so if you look at the things in red, I've determined that somehow when my molecule breaks apart, I get an ethyl group, I get an aromatic ring with 1 substitution, and I get an acyl group. So those are my 3 pieces that I have here. How does that all come together? So just to summarize, these are my 3 fragments. Those are the 3 pieces that I have. So if I add all of those pieces up together, I would get 11 carbons. Whoops, I only have 9 in my formula. And that just means that some of the fragments, things can end up in 2 different places. So it's likely, my proposal is that the ethyl and the acyl are actually just splitting on either side of the carbonyl. Let me show you what I'm going to propose. I'm going to say this, right? I'm going to propose this because this has an ethyl group, it has an acyl group, and it has my ring here. So if I split on this side, I'm going to get the 5-membered ring, and I'm going to get the acyl. If I split here, I'm going to get the ethyl, and actually a peak that weighs 105. So splitting here would give me that 105 peak, the base peak. Okay. Now, I don't know about you, but when I first learned this and I looked at it and went, that's pretty. How am I supposed to do that on my own? I'm walking you through this again in the exercise, and I'll be helping you with that. And I have more examples of this for you to work on. There's also some other things. Once you kind of know where that comes from, you can look up what are common groups that match some of these masses. So these tables are out there. You can just Google mass fragments or mass spec functional groups or something like that. And so I could look at something like that and I could say, well, you know, something that weighs 57, that's an acyl group. Is it possible that I have an acyl group? Something that weighs 29, okay, I got 2 options here. So when you work through these, we are not going to try to do the mass spectrum of DNA or of a huge steroid or Taxol or something like that. Our molecules are going to be simple, but it will give you that foundation that you can build on. So in Chem 204, we can do a little bit more and things like that, okay? All right, questions, anything in the chat really quick about mass spec? As again, I'm gonna come back to it, I'm gonna refer to it. We'll look at it in the experiment itself. But we're gonna look at our second technique today, which is infrared. And okay, can I go to the slide with the fragments? This one here? I assume this is the slide you want. Oh, one more. The logic of the fragments. You can unmute too and ask. And I will post this right after class.
Yeah, I just wanted to see it again. Thank you.
I hope you like problem solving in jigsaw puzzles because that's what spectroscopy is. All right, so let's look at infrared spectroscopy. So this complements, you'll notice when we did mass spec, several times I said, well, infrared told us something. So useful technique for that. And I just want to take a moment and remind you of something very basic about spectroscopy. Right, so what we're going to do with electromagnetic spectroscopy is we're going to shine electromagnetic radiation, shine light on our sample. We shine the light on the sample absorbs some of that light, we look at what came through. We look at what came through compared to what we put in, we can say what was absorbed there. And this is kind of the key to this spectroscopy, and I want to get this in your head again because it's going to help this week and next, which is that if a photon is absorbed, then we know that there has to have been some sort of an energy transition in the molecule that corresponds to the energy of that photon. Again, we're trying to learn about things that are too small to see with the human eye. They're too small to see with visible light for the most part. So we shine light of other wavelengths on it. And if the molecule absorbed that photon, then the energy of that photon corresponds to some sort of an energy change within the molecule. So just by knowing that it absorbed a photon of 880 nanometers, we know that somehow there has to be an energy, transition of 880 nanometers in the molecule itself. Okay, so we can imply something about the molecule by knowing what it absorbed. You could also excite the molecule, woo, excited molecules, and look at what light's emitted. This is what you did with the atomic spectra back in Chem 150 when you looked at the hydrogen lamps and the helium lamps and things like that, and they gave out certain colors. And this figure here is so simple, but it's the key to all of what we're doing, which is somehow you have a change in energy in the molecule. That change in energy, we know E equals h nu, corresponds to the photon that was absorbed or emitted, okay? So I'm hoping that's pretty obvious, but it is an important thing that saying if that photon was absorbed, the molecule had to change energy in that way. So now I can know something about the energy of the molecule or how my molecules put together. So that's kind of a little background theory there, but it's an important one to remember. Our good old electromagnetic spectrum, you've all seen this many, many times in your life. And so up until this point, for the most part, what we've done is UV vis spectroscopy, and that's electronic. That's saying, where are the electrons moving, right? Are we moving from an S to a P, or from the N is equal to 1 shell up to an excited state, N is equal to 5, something like that, okay? So that gives us our colors of our compound. So we've done that. Infrared spectroscopy that we're going to look at today, right? That's just energy that's of a lower wavelength. Instead of exciting electrons, this causes the molecule to vibrate and shake within the molecule. So molecular vibrations is what we're going to look at here. This class, we're not going to get into microwave radiation, but you can. It looks at rotations through space. You can actually get a lot of information about how a molecule rotates. This is actually really common in astrochemistry. Looking at molecules in space and other stars, when they say, hey, we found a molecule in the surface or in the atmosphere of Venus, this is probably what they did, is they looked at microwave radiation there. And then next week, we're going to look at radio waves. We're going to go way down on the spectrum, all the way down to the end to the radio waves, because it turns out when a molecule absorbs radio waves, you're actually changing the spin of the nucleus itself. So, right, the nucleus is all protons. It has a positive charge. It's spinning. You can change its spin just like you could, well, don't change the Earth's spin because we'd all die. But you've got any sort of a thing spinning like that, you can rotate it one way or the other. And so we'll look at that next week. So same idea, they're all absorbing electromagnetic radiation and it causes a change. When we did UV vis in class before, looked at like colored compounds, it changed electrons. Now we're gonna change the vibrations. And so let's talk about covalent bonds just for a minute. And we built a few misconceptions in for you, unfortunately, that I wanna try to fix. So if you think about a single bond and what a single bond can do, all right? A single bond actually has two types of motion it can do. We talked in class a lot about rotating around a single bond, right? That's where you get conformers and Newman projections and eclipsed versus non-eclipsed and things like that, right? We've done that. The other thing a single bond can do is it can vibrate, and it vibrates like a spring. Every chemical bond behaves like a spring. We draw it on the page. We tell you the bond length because that's the average length. That's the most stable, but it always can vibrate a little bit. So a single bond can rotate and it can vibrate. A double bond, well, it can't rotate, it's locked in place. So all it can do is vibrate, but it can still vibrate, and so you can do that. So let's think about a simple molecule. Let's think about water for a second. Water, H2O, right? You guys know that. What can it do? What are the possible types of rotation or, vibration it can do? Well, you've got your oxygen and you got two hydrogens. Couple options you could do. Those hydrogens could both move in towards the oxygen and out at the same time. So they could do a symmetric stretching. They could do an asymmetric stretching. This is always, IR is always making the professor do funny dances. It turns out they can actually, I'm going to show this on Spartan in a second, it's easier. They can bend in and out. So you've got your hydrogens, and that bond angle can actually change. We told you 109.5 or 104 in water, and it is, but it actually is an average. It actually moves. So you've got three different ways that can move. All right, and that's what we're going to be looking at. Now, those vibrations that a molecule does occur at a particular frequency. If they occur at a particular frequency, that means that the molecule will only absorb a photon that matches that frequency. Ooh, hey, connection to spectroscopy. So what affects that frequency? Well, the frequency of the vibration depends upon the shape of the molecule. It depends upon the masses of the atoms on either side. Is it a single bond versus a double bond? So hopefully what you're seeing is just by looking at the vibrations, I can tell an awful lot. I can tell things about shape and mass and types of atoms and types of bonds, all those things that really give rise to functional groups. We're talking about a carbonyl as a carbon and an oxygen with a double bond. Or an alcohol is an oxygen and a hydrogen with a single bond. And one of the big take-home messages about infrared spectroscopy is it tells us about functional groups, what functional groups are present in our molecule. This can be really useful to know. All right, now it is important to mention this, that vibrations will only show up in the IR if they change the net dipole of the molecule. So molecules that are polar, if the vibration changes that net polarity, then it shows up in the IR. Even molecules that aren't normally polar, like carbon dioxide, and I'll show you this here in a moment. Carbon dioxide, right, it's got polar bonds, but because it's symmetric, they cancel out. But if you do an asymmetric stretch where one oxygen is moving in and one oxygen is moving out, then that actually can change that dipole because the bond distances aren't the same anymore. If it doesn't change the dipole, can we still see it? Yes, you just have to do a different type of spectroscopy. It's called Raman spectroscopy. We're not going there. Chem 205, we'll go there if you are curious about Raman spectroscopy. Okay, so let's look at a couple of these. This is easier looking at it than it is trying to describe it because it's a motion. So let me pop over here to Spartan, and hopefully it's going to continue to work for me. Yes, I'm on the VPN. All right, so here's carbon dioxide. Okay, well, no. All right, so here's our carbon dioxide molecule. Now, this is a nonpolar molecule. Carbon and oxygen don't have the same polarity, but remember that you've got a polar bond here and a polar bond here. They just end up canceling each other out. All right, let's look at this. So this squiggly thing up here is a spectrum. I can click on the spectrum, and I've already done the add, and I added the IR here. And so this is the spectrum. I still get a couple of peaks in here. Now with Spartan 8, there's this little button on the left that looks like a little spreadsheet. If you click on that, it shows you all of the peaks. And it's a little bit weird because it showed two of the same and then one that has no intensity. I'm not sure why it did that. But if I click on this box, that's this peak here, and I can see what it is. Okay, you can see the molecule actually vibrating. I love the fact that this actually vibrates here. So this is an asymmetric stretch. One of the carbon-oxygen bonds is getting shorter while the other one's getting longer. That is going to change the net dipole. So that shows up in the infrared. Likewise, a WAG. And so I can move it around and see what's happening here. Let's see that molecule a little better. Doink it, doink it, doink. So the molecule is actually bending. Okay, so everything we told you exactly about it being static is not true. The only time molecules are static is at 0 Kelvin. Okay, now we talk about it at temperatures above that, them moving through space, and they do, but not just move through space. They actually vibrate as well. And now let's look at water. We said, whoa, that's a big water. Okay, we said there were 3 ways that water should vibrate. And in fact, we see 1, 2, 3 peaks here. All right, so let's look at those 3 peaks. What are they? Okay, this is what's called a scissor. That's the bond angle coming in. This is what I was trying to do a minute ago. Yeah, it's much easier just to see what the molecule is doing there. Okay, and then you've got the symmetric stretch. Doing, doing, doing. That's the hydrogens moving out at the same time. And you have the asymmetric stretch. So notice that the type of stretch is at different frequencies, right? So we're starting to see those things there. Let me show you one more molecule here, and that's methylene chloride or dichloromethane. That's DCM, that's the solvent we keep using. One thing I hope you're noticing is as I went from 3 atoms up to 5 atoms, I have a whole lot more transition or a whole lot more vibrations here. So more atoms gives you more types of vibrations. And we can do a couple things. So let's look up here at, say, 3114, 3104. And what is this? Well, that's the asymmetric stretch of my hydrogens. Okay? I can go down here. Let me see if I can find it. That's symmetric. There's the asymmetric stretch. Looks like it's listening to, I don't know, cool jazz or something. I don't know. And so one thing I want you to notice here is you can either have the hydrogens doing the asymmetric stretch, or you can have the chlorines. They both do it, but notice that they're incredibly different wavelengths or incredibly different energies. When the hydrogen does it, it's up here at 3,104, but when the chlorine does it, it's down there at 714. Why? Because a chlorine is much heavier. So it's going to vibrate at a very different frequency. Think about a spring in physics class when you put heavier weights on your springs than lighter weights. So the mass of the atom changes that frequency quite a bit. And there's all sorts of things that's got a twist now you can do. You've got a WAG. We actually call it a WAG. You've got the symmetric. I swear that this is where Fortnite came up with some of their dances for some of these things here. Because these are, okay, a lot of different things that you got going on there. But it's an active process, which is why showing it with Spartan is a little bit easier there. Okay, so what can we conclude from that? What do these spectra look like? Let's keep moving on here. Okay, to actually look at some spectra. All right, I'm running a little behind, so I want to do this. Okay, so how many vibrations for water? Turns out, again, we got one more formula. Yay, we love formulae today. And if you've got a linear molecule, then you have n atoms give 3n minus 5 degrees of freedom or vibrations. If you have a nonlinear like water, then n atoms would give you 3n minus 6. Well, n was 3, so 3 times 3 is 9. 9 minus 6 is 3. So we should get 3 ways your molecule can vibrate, which is what we got. Methylene chloride went up to 5. So we had 3 times 5, that's 15. So we end up with 9. So you, as you can see, as you increase the number of atoms, you increase the number of possible vibrations. Again, the vibration's only going to show up in the IR if it changes the net dipole. And every once in a while, they end up overlapping and some things like that. So you won't necessarily always see that number of peaks, but it gives you a good idea about what you should see here. Okay. All right, so let's look at a couple other thoughts that we've already done, and I just kind of want to mention it. One of the things you'll notice that's very weird about an infrared spectrum is the units that we use. We use a region, and we look at the region from 4,000 centimeters to the -1 to 400 centimeters to the -1. What happened to wavelength? It's inverse wavelength. They're called wave numbers, or centimeters to the -1. Why do we do that? Well, we do that because remember, the longer the wavelength, the lower the energy. And so by taking the inverse, higher numbers mean higher energy again. That's why we do it. So if it's vibrating at 4,000 centimeters to the -1, then it is higher energy than something that's vibrating at 400 centimeters to the -1. So they took the inverse so that high numbers mean high energy again. There you go. I guess chemists don't want to compute things in their head. Really, the physicists started this, so we'll blame them. Then the other thing I said a minute ago when I showed you hydrogen versus chlorine is that frequency is affected by mass. So here I have 2 infrared spectra. One is of CHCl3 and the other is of CdCl3. So we changed a hydrogen for a deuterium. Remember, a deuterium weighs twice a hydrogen. So my carbon to hydrogen stretching should be changed. And you'll notice here is the red one, and then here is the blue one that corresponds to that. So it shifts to a much lower energy when I change the mass. Likewise, this shifts to a lower energy when I change the mass. So heavier things will vibrate further down. That's what, I guess that's the take-home message there. And so that will help us with that, okay? Just a couple other quick things. This is one thing that as a student drove me absolutely batty about infrared, but the intensity of the peak depends upon 2 things. How many bonds have that particular frequency, but also how much the dipole happens to be changing for that particular vibration. The result of that is you could have multiple types of bonds, but one changes the dipole more, so its intensity will be greater. So you can't correlate how many bonds you have to how big the peak is, right? We're so used to saying this is a bigger peak, so it has more. You can't do that with IR. The intensity of the peak is essentially meaningless, with the exception of a carbonyl peak that'll come up in a minute, because there always has to be an exception. But for the most part, if you see a band that's bigger than another band, it does not tell you you have more of that in your molecule. You can't do that. So it's non-information. So just kind of get in your head, and for infrared, the intensity of the peak does not tell you very much about concentration. Okay? Weird. I hate that, but it's true. That's just reality. All right, so just to show you some examples of other things I've said, bond strength should affect the frequency, because the stronger the bond, the tighter the spring you're trying to vibrate, so the more energy required to vibrate it. So a single bond will be easier to vibrate than a double bond, which is easier than a triple bond. So you can see here, this peak right here is our carbon-carbon double bond. And then this peak right here is the carbon-carbon triple bond. So you can see that going from a double to a triple increased the frequency. Now, what about my single? I didn't start there because it turns out the single is actually that little peak right there. Again, the intensity doesn't tell you anything, but there's your single bond, then it moves up to the double bond, then it moves up to the triple bond, okay? So where it shows up is affected by that. So what do we have right now? We have the fact that different masses vibrate at different locations. Different bonds vibrate at different locations. Turns out different geometries will vibrate at different locations depending upon kind of wags and things like that. So people have gone through and they have taken the infrared spectrum of pretty much every molecule that they could find. And I'm not kidding, there are books of just these spectra. And what they've done is they've created correlation tables. Yay, somebody did this work for us already. They said, you know what, if we look at all the molecules in the world, well, all the ones we studied, on average, we find that CH bonds, if it's an alkane, they show up around 3,000 to 2,800. If it is a bend, if it's a CH3, it's around here. If it's a CH2, it bends around here. A CO, all right? And if it is an alcohol, an ester, an ether, or carboxylic acid, you're gonna show it right around here. But if you have an alcohol, you get this really broad peak. And there are some terms here, M, S, and W, that's strong, medium, and weak. So you can kind of see some things here. An amine, look at this. If it's a primary amine, you get 2 bands around 3,300, but a secondary amine would only give you 1 band around there. So you can see that the functional groups are correlating to lines we see. In fact, you can also look up at bifunctional group. What if I have an amide? What should I see? Well, if you have an amide, you should see these things. You should get a stretch in 1600. You should get an NH stretch here and an NH bend there. So people have done this for you. These correlation tables are available on the internet. They would always be available to you. Please do not memorize the correlation tables. You have far better things to do with your brain. So you can always look these up. And that's what we do. We correlate our spectrum to these tables. So some people call them lookup tables, depending upon how much programming you've done. Okay, so here we go with our a spectrum. I do want to differentiate 2 parts of the spectrum, what's called the simple stretching versus the complex stretching. It's squishy, the line's around 1500, but that's not exact. But for the most part, 1500 and above corresponds to a single type of stretching, a single functional group. 1500 and below is often the entire molecule moving. So we call it the fingerprint region because every molecule, when the whole molecule vibrates in a different way. And so I will show you that with a molecule here in a minute. But the point that I'm trying to make is you can try to identify what the stretches are above 1500. You do not try to identify what the stretches are below 1500. But every molecule will have a different pattern below 1500. So how do you interpret one of these? You sit there, you look at it, you go, what am I looking at? You look for characteristic things. You look for, use the correlation tables. What peaks do I see that might correspond to an alcohol or something like that? So we got a nice peak here. You almost always see this one at about 3.5 or at about 3,000 here. This is the carbon hydrogen stretches and carbon hydrogen bends because we're looking at organic molecules. Okay, let me show you a couple of these to give you some idea. Here are, these are what alcohols look like, alcohols and amines. If you have an alcohol, it always has this really broad absorption around 3,400, okay? So if you look at your spectrum, you see that broad peak there, you know you've got an alcohol. Likewise, an amine gives you a single spectrum, a single one that's sharp. Notice the difference. This is huge, it's broad, it's wide. This is a single one. You can look at the correlational table and you see a minute ago, if you only got 1 absorption there, then it had to be a secondary amine. So this, as it turns out, is going to be, oh, look at that, a nitrogen that's got 2 of these groups on it. It's a secondary amine. So you can tell some things like that. So a single spike out there. A couple others to look at just to be familiar. Carbonyls. I said carbonyl was the one exception to the intensity because a carbonyl is almost always the biggest stretch in your spectrum. If you have a little tiny thing up here, it's not a carbonyl. Carbonyls are huge. They go all the way down to the bottom. And they're around a little above 1,700 for the most part. They're really distinctive. So you can see those really quickly. Okay. So you will be asked in your post labs to annotate a spectrum. What does it mean to annotate an IR? It just means, oh, my font's moved a little bit. It just means that you highlight the major point, the major peaks. You don't, you just say like this peak here, that's a carbonyl. This peak here, these are the NH2 stretches. So you're just highlighting the major peaks and saying what structure or what they correspond to in your molecule, okay? You don't have to draw the list structure. I just put that on so you can see what the molecule came from when you're studying from this later. With an NMR, we do start with the list structure. We don't for IR. So you just say, this peak, that's a carbonyl. This peak, that's a carbon hydrogen. There. Okay. Let me do this one other thing with the fingerprint region. I said that region down at the bottom is what we call a fingerprint region. Why is it that? So here is everybody's favorite molecule, caffeine. Okay. Now caffeine has a lot of atoms, so we should get a lot of vibrations. There we go. And we do. We get a lot of vibrations here. So when we look up here at the high end of the spectrum, you can see that it's a very specific rotation or vibration that's happening. This is the CH stretch of that methyl. I can describe that. I can say that's the carbon-hydrogen stretch on the methyl. I could describe this one probably. Well, no, that was a little harder. There's the twist on that methyl. That one I just keep picking that methyl. Why do I keep picking that methyl group? There we go. There's another methyl group. Okay. So those are ones that are individual. What happens though if we come down here into this region here, below 1500, the fingerprint region? Let me drop down here. Okay. And you see what's happening here is the entire molecule is vibrating. So I can't describe that as like the carbon-carbon bond or anything like that, because the whole thing is moving. So every whole molecule is going to move in a different pattern though. So caffeine always looks like this down here. So we can use it like a fingerprint to identify it against a known, but you cannot go through these down here and try to pick out absorbances. I can't look at this and say, oh, there's a carbon-nitrogen bond there. Now, if I know there's a carbon-nitrogen, I can start to kind of look for that, but you can't go the other way. Okay, let's look at an example. So here is an IR, all right? I want to look at just one here, and then we're going to be done because we're almost here at our hour. So at this point in your academic career, when you look at an infrared spectrum, I'm going to give you options. I'm going to say it's one of these 5 molecules. We will get to the point where we can use NMR and IR, or IR and mass spec together, like I did at the beginning of this presentation. But right now, when we're first looking at IR, I'm going to say, what do we got? All right, so I want you to take a moment, or I want you to just kind of look at it and see if you can at least narrow down a few things, right? So pause to get some of that caffeine. All right, so what do we do when we look at it? Well, I'm going to walk you through this, but as a trained chemist, which you are on your way to being, end of this class, you can put that trained chemist badge on there for IR, NMR, and mass spec. First thing I notice is this thing here, this broad peak around 3,400. This is probably an alcohol. The other thing I notice is I don't have a really big peak around 1,700. So I probably don't have a carbonyl. So knowing that right away, I've already eliminated all but 2 of my options because I have an alcohol here, or likely have an alcohol. So I'm probably going to be D or E. Okay, so you can see that that gives you. So let me walk you through all of those though. Oh, that is not what I meant to do. Okay, click the wrong place. Okay, so let me walk you through the logic. I keep clicking on the picture and it's hyperlinked, sorry. So we can actually start with our unsaturations, which is useful. So if you do the C5H10O and you plug it into that formula, we get 1 unsaturation. So that means somehow I either have to have a ring or a double bond, all right? So that actually eliminates D right off. Okay, so that rules out D, because if you do the molecular formula of D, it doesn't have an unsaturation, and that's actually C5H12. Whoops, that's the wrong compound. And that's one of the things in unsaturation. Without having to count through all of the possibilities, unsaturations helps you with that. So it can't be D because that's got the wrong formula. Then I do what I just said a minute ago. I look at that really broad peak around 3,300 and I say, you know what? That's probably an alcohol. And so the broad peak at 3,300 tells us that we have an alcohol. And the lack of, all right, sorry. So that means my only option is E. And then the lack of a carbonyl tells me it also could not be A or C. So I'm left with B, right? Because B would have 1 unsaturation. But B doesn't work because B doesn't have that alcohol group. Okay. That makes sense? I looked at it, I saw an alcohol, I saw no carbonyl, then I was able to narrow down what it was. So as I say, for IR right now, we're going to be at this level. We will get to the point where we can take a mass spectrum and an IR together, and we can come up with a molecule. But today and this first week, when you're first working with IR, I'm going to be giving you options. I'm going to say it's one of these 5. Which one is it? To help build those skills up for you. And then we'll build it in from there. Okay. So the great IR summary here at 11:01 a.m. is that it looks at molecular vibrations that change the dipole. But the TLDR for IR is that it finds functional groups. And you use the correlation tables to do that. and the fingerprint region is for confirmation. And that's it. That's my presentation. So that is infrared and mass spec in a nutshell. As always, I will stick around to answer questions that you might have about what we just covered. But this ends the official pre-lab portion of your morning. I sound like I should be working in an amusement park or something. Please keep your arms and hands inside the ride at all times. All right. Stop talking, Dr. Mulford. Have a great Friday and a great weekend.